So when you're solving a system of equations, either in a circuits class or when you're trying to determine if a vector is in the range of a transformation or anything of that nature, when you're trying to go through that process, it's useful to have some information in advance about what kind of solutions and how many solutions you should expect to receive after the matrix has been solved. As we mentioned, it's pretty uncommon in the real world to be solving these systems of equations by hand. Typically, in the real world, when you're solving these systems of equations, you're using software to help you to do it. And particularly in engineering, the industry standard software that we use in most mathematical calculations is a piece of software which is called MATLAB. Now, when you're using computers to solve math stuff for you, you need to be able to communicate with the computer, right? You need to be able to type stuff into the computer that will allow it to produce what you're looking for. And you also need to be able to read and understand the results that the computer gives back to you. So as you're solving systems of equations in MATLAB, you're going to be using this method which is called lin solve, lin for linear, solve for solve. And let's go through the documentation for this particular method in MATLAB, and let's have a look at a bit of the language that's being used in the documentation for this method. So for example, here in description, x equals lin solve a comma b solves the linear system a times x equals b. I want to draw your attention to something right down here at the bottom of this description paragraph. It says, lin solve will throw a warning if A is either ill-conditioned. We're going to talk about a matrix being ill-conditioned in a couple of weeks. It also will throw a warning if the matrix A is what's called rank deficient. Rank deficient. So today I want to talk about what this phrase rank deficient means in this error message and what consequences it has on solutions to linear systems like you would be solving, for example, in MATLAB. So imagine we have a matrix A, and let's call A with a tilde, A tilde. We're going to call that the matrix A after it has been row reduced, the matrix A after it's been converted to row echelon form. If someone speaks about the rank of the matrix A, the rank of the matrix A is equal to the number of pivots in A tilde, the number of pivots that are left in the matrix after it has been row reduced. This is what we call the rank of the matrix A, the number of pivots left after the matrix has been row reduced. So to give you an example, suppose let's take this matrix A that we used in yesterday's video. A is equal to the matrix with 3 rows and 2 columns. Here 2, 4, 3, 0, negative 1, 1. Someone asks me, what is the rank of this matrix? The first thing that I would do in answering this question is I would find the row echelon form of this matrix. What the definition is calling A with a tilde on top of it. Now, we found the row echelon form of the matrix A in yesterday's work, in yesterday's video. The row echelon form of the matrix A is what's given by this result down here, the portion of this augmented matrix that's to the left of the bar. This guy on the left is where A tilde lives. So having now obtained the row-reduced version of the matrix A, I'm going to now look inside this row-reduced version of the matrix A, and I'm going to count how many pivots we've ended up with in that row-reduced matrix. So I see, for example, a pivot here in the upper left, and I see here a pivot in the second row and the second column. So here I have 2 pivots in A tilde. So because I have found 2 pivots in A tilde, what I would say using the new language is that the original matrix A, has rank 2. Rank 2 because after row reduction, it ended up with 2 pivots. The matrix A has rank 2. So now that we've talked about what is the rank of a matrix, let's talk about these terms rank deficient as used in the MATLAB documentation, as well as the sort of opposite of that, full rank. First of all, an observation. If you have a matrix A with m rows and n columns, then the rank of the matrix A must always be less than or equal to whichever of these two values is smaller. The rank of the matrix A must always be less than or equal to whichever is smaller, the number of rows slash the number of columns, less than or equal to the minimum of those two values. So for example, if you have a matrix A that has 2 rows and 3 columns, then the rank of the matrix A must be less than or equal to 2, 2 being the smaller of the values 2 and 3. The rank of the matrix A must be less than or equal to 2 in this case. Likewise, if your matrix A has 5 rows and 3 columns, then your rank has to be less than or equal to 3 in this case. The rank must be less than the smaller of these two values. And that's just because rank is coming from having a certain number of pivots in your reduced matrix A tilde. And if you're looking at your reduced matrix A tilde, there are only a certain number of places where a pivot can actually go in A tilde. There's maximum 1 pivot per row. There are only so many pivots that can fit in a matrix of this size. And in particular, if your matrix has 2 rows and 3 columns, you cannot fit more than 2 pivots inside the reduced version of that matrix. The same thing is true if you're in a situation of having 5 rows and 3 columns. When you row reduce something like that, there are limits on the kinds of results that you can get from that kind of row reduction. If you've got 5 rows, then maybe you have a pivot here and zeros underneath that. Maybe you have a pivot here and zeros underneath that. Maybe you have a pivot here and zeros underneath that and some other values elsewhere. But again, there are only so many spaces where the pivots can fit in a matrix of this size. So if your matrix has 5 rows and 3 columns, you cannot fit more than 3 pivots inside the reduced version of that matrix. So you have a cap on the rank of a matrix of a given size. So when we talk about a matrix being full rank, that means that you have as many pivots as you possibly can. The rank of A for a full rank matrix is as big as possible. So in the case of a matrix with 3 rows and 3 columns, full rank would be that your matrix has a rank of exactly 3. You have 3 pivots, you have as many pivots as you can possibly fit in a matrix of this size. Likewise, this matrix A would have full rank if A tilde had 2 pivots, if you had as many pivots as you could possibly fit in a matrix of this size. So full rank means you have as many pivots in A tilde as you possibly can. By contrast, your matrix is going to be rank deficient if the A tilde has fewer pivots than you could possibly fit in a matrix of that size. Rank A is smaller than the minimum of the number of rows and the number of columns. So that would arise in a situation, for example, where your A tilde maybe looked like this. You have a pivot in the upper left corner, but the bottom row doesn't have any pivots inside of it at all. This matrix A would be considered rank deficient because the matrix A would have 2 columns and 2 rows, but it only has 1 pivot in the A tilde. So this would be rank 1, So the matrix A in this case would have rank 1, which is strictly smaller than what it could be, strictly smaller than the maximum possible rank, which is 2. So now let's think about what rank and rank deficiency implicates in terms of solutions to equations and systems involving the coefficient matrix A. So scenario number 1, suppose that we're dealing with a system of equations where the coefficient matrix A is rank deficient. So the rank is less than what it could be. If you're in a scenario like that one, what can we predict about solutions to an equation of the form ax equals b? Or in other words, what can we predict about systems of equations involving A as the coefficient matrix? So let's go back through some of the calculations and the work that we have done up to this point, and let's examine scenarios where we had a rank deficient coefficient matrix. And let's see what happened in the case that our matrix was rank deficient. So let's, for example, go back to this system of equations from several videos ago, from this lesson representing systems using matrices. Here, this system of equations gets translated into this augmented matrix, where we have the coefficient A on the left side, and then we have some output vector B on the right side that represents the values that we're trying to get out of this system. Now, in this video, notice that our coefficient matrix A has 2 rows and 2 columns. So the maximum possible rank in this case would be rank 2, because 2 would be the maximum number of pivots that could theoretically fit in a matrix of this size. However, when we row reduced the matrix in this problem, and we arrived upon A tilde here at the bottom of our calculations, A tilde only ended up with 1 pivot inside of it. A tilde, the matrix on the left-hand side here, only has the pivot in the first row, and in the second row, the coefficient portion of the augmented matrix has all zeros. The pivot of the augmented matrix is in the outputs column. It's not in the coefficient part of the augmented matrix. So because of that, this is a situation where our matrix A is rank deficient. And let's see what consequences that had when we were solving this system of equations. In this case, when we solved this system of equations, we ended up with an inconsistent system. We ended up with a system of equations that had no solution. And that's because on the left-hand side, we had this row of zeros attached to A tilde. And on the right-hand side, we had a non-zero value. So this formation in the bottom row of our augmented matrix corresponds to a requirement 0 equals 4, which is impossible. So in this situation, our equation had no solution. So that's one possibility that can arise when you're working with a rank deficient matrix. When you're working with a rank deficient matrix and you're trying to solve a system of equations where that rank deficient matrix is the coefficient matrix for your system, there is a possibility that when you solve the system, there's actually no solution at all. So that's one possibility in the rank deficient case. The other scenario where we found ourselves dealing with a rank deficient matrix, and in fact the exact same matrix A is in this problem as in this one. The coefficient matrix in this is the same, it's just the output vector that's changed. Once again here, our matrix A is rank deficient because we have a maximum possible rank of 2 for the coefficient matrix A, but the actual rank turned out to be 1, which was strictly smaller. And this is another situation where the solutions to this system ended up being a little bit weird. In this case, again, because A was rank deficient, we got this line of zeros here on the bottom of the matrix. And in this case, because we had both zeros on the left-hand side and zeros on the right-hand side, we ended up with a system of equations that had infinite solutions. So these are two possibilities that have occurred when dealing with a rank deficient coefficient matrix. We have seen a possibility that the system has no solution, and we have seen a situation where the system has infinite solutions in these two examples. Let's consider a few more examples from the work we've already done in previous videos. So in this problem, someone had a matrix and they row reduced it, and the row reduced version of the matrix was given right here. Let's do this one. And the A tilde in this problem, the coefficient portion of this augmented matrix, this is 3 by 3 matrix over here on the left side. So this would be the row reduced coefficient matrix A tilde in this problem. Now notice that this coefficient matrix has 3 rows and 3 columns. But after row reduction, we only ended up with 2 pivots on the coefficient side of the augmented matrix. So once again, this is a situation where the coefficient matrix has only rank 2 out of a max possible 3, and this is another situation where we ended up with an inconsistent system, a system that had no solution. Scrolling down a bit to another example that we worked in a previous video, again here, this is an instance where the reduced coefficient matrix A tilde only has 2 pivots out of a maximum possible 3. So this matrix A would also be classified as rank deficient. And in this situation, once again, we found ourselves with infinite solutions. So let's summarize some of our observations and findings. In general, when you're solving a system of equations, or when you're solving a matrix equation, there are 3 possibilities that we have encountered in terms of the solution set. We have encountered situations where we have one unique solution. We have encountered situations where we have no solutions. And we have encountered situations where we have infinite solutions as a result of having at least one free variable. So these are the 3 possibilities that can happen in general, but when our matrix A was rank deficient, we only encountered cases where we had no solutions or infinite solutions, depending upon what was happening in our output vector and whether the outputs column ended up with a pivot inside of it or not. So when you're dealing with a matrix that's rank deficient, this option of one unique solution is off the table. This one doesn't happen, and the 2 possibilities that you are left with is that this system of equations has either no solutions or infinite solutions. So in light of that, we can now imagine why MATLAB might throw an error in a situation where you're trying to solve an equation involving a rank deficient matrix. Now suppose in particular we're dealing with a rank deficient coefficient matrix and we're trying to solve the matrix equation AX equals specifically 0 on the right hand side. If we're in a situation like this, what can we predict in terms of the solution set to this equation with a 0 on the right hand side? Now, remember, in general, when we're solving matrix equations, there are only 3 possibilities. There's the possibility of having a single unique solution to the equation. There's the possibility of having no solutions to the equation. And there's the possibility of having infinite solutions to the equation. Now, given that our matrix A is already deficient in its rank, we have already eliminated the possibility that there's one unique solution to this equation. So that's off the table. But let's also think about whether it's possible to have no solutions to this equation. I think in this particular case, we can also cross off the possibility that there are no solutions. And that's because remember that a matrix always has at least one vector in its null space. A matrix always has at least one object in its kernel, at least one object that always becomes zero after the matrix is applied. And that is what we called in the previous video the trivial solution, which is the zero of the domain. So that eliminates the possibility that there are no solutions. This is a situation where there must be infinite solutions if the matrix on the left is rank deficient and we're trying to get zero on the right-hand side. So that concludes this lesson on matrix rank and on solutions to systems. We said that the rank of a matrix is the number of pivots that are left in the matrix after it has been row reduced. In general, a matrix has the property that its rank cannot be any larger than the number of columns slash the number of rows, whichever of those values is smaller. So when a matrix is full rank, that means that the rank is actually equal to its maximum possible value. And when the matrix is rank deficient, that means that the matrix is always smaller than its maximum possible value. And what you see happen is that when you're dealing with a rank deficient matrix, you end up with kind of weird solutions to matrix equations. A rank deficient coefficient matrix means that you're going to end up with either no solutions or you're going to end up with infinite solutions to the system, depending upon whether your outputs column ends up having a pivot inside of it or not. A rank deficient matrix always has a null space that has infinite vectors inside of it. Both the zero vector is in the null space of this matrix, and also there is an infinite collection of other vectors inside of this null space, coming from this equation having at least one free variable that's giving you infinite solutions. So that's why we need to pay attention to rank when we are solving systems, particularly when we are solving systems using computers. Because if your matrix is rank deficient, your software will struggle to solve the system because the system doesn't have a unique solution. It might not have a solution at all. And so this is the situation that arises typically when you do not have enough data or information about your actual real world scenario to solve that situation effectively. Typically, you will have to go back out into the field, collect more data, collect more measurements, apply more physical laws in order to get enough information to build a system of equations that actually is full rank.